Hi, I'm Tim Kelton. I'm a director of software engineering at Aurora Innovation. And joining me shortly will be Stefano Marzani, and he's the worldwide tech leader in autonomous driving for AWS. And at Aurora, we're focused on bringing the benefits of self-driving technology to the public safely, quickly, and broadly. We're building what we call the Aurora Driver, and this is a combination of hardware and software that provides a driver as a service. So before our trucks drive a mile on the road, the cloud plays a big part in how we build the Aurora Driver. So that's part of the story I want to share with you today. And my hope is that you'll come away with some ideas of how similar approaches can be expanded for your organization. And self-driving is a hyperscale problem domain, and we need to leverage the latest advancements in AI and machine learning, but we also collect massive amounts of data for every mile driven, and we need mature, scalable tools that gather insights from that data and scale to meet our needs. These technologies all need to work seamlessly together to help us move quickly. And you can think of Aurora Driver as approximately broken up into subcomponents of sensors, perception, planning, and high-definition maps, all working together in unison. We test them on the road, but our on-vehicle road testing is just not enough. We need the ability to virtually test the exact situations the Aurora Driver faces on the road, but we need to do this virtually in the cloud. And the reason virtual testing, or what we call simulation, is so important to Aurora is because we believe it's the best way to fully understand how the Aurora Driver is progressing. Consider the number and variety of experiences that a vehicle can have on the road today. It's vast. And if you want to understand the implications of a single change to the Aurora Driver's code base over all of those experiences, we estimate you'd need a 100-vehicle fleet operating for 10 hours every day, and then you need to run that for 50 years. That's just not scalable. And we change our code on our main branch of our monorepo more than 200 times every single day. So at Aurora, every code change is run through a number of offline tests in the cloud, including simulations and perception scenarios, to recreate all the experiences that are most relevant to that change. So this gives us really fast feedback on how those changes modify performance. And so thus, we run around 5 million simulations at Aurora every day. Naturally, this requires incredibly powerful and reliable cloud computing infrastructure. So that's part of why we're here. Aurora's cloud infra enables developers without backgrounds in high-performance computing, distributed systems, to be able to dynamically scale any simulation workload across thousands of compute nodes. So the number of simulations we run, it's accelerating. See the curve in the graph. And as we build more scenarios and we hire more engineers, we're commissioning more sims. So we've run over 1 billion simulations in just the last 2 years. And over the life of Aurora, we calculate that at least 6 billion miles of driving would have been required to expose the Aurora Driver to that same number of experiences we've given it with our simulations. We also need our software stack to be architected in a robust way that supports repeatable behavior in simulation. Our simulations are deeply integrated with the Aurora Driver software stack that runs on the vehicle. So if you think of the Aurora Driver as broken up by those subcomponents of sensors, perception, planning, and high-definition maps, then in simulation, we run these same software modules unmodified. Furthermore, we can choose to test all of them end-to-end, or we can take certain modules out and replace them with synthesized versions, helping us test, for example, motion planning in isolation. Some of our more common sim configurations are shown here. This flexible architecture allows our simulator to test and train our motion planning system, to test and train our perception system, allows us to prototype our sensor hardware, and test our maps. So to give you a better actual visual picture of what this looks like, we're going to go deeper into one specific configuration where we simulate the sensors to help us evaluate our perception system. And to reliably test the Aurora Driver's perception system in simulation, we must be able to model the sensor inputs. And these are LiDAR, our radar, and our cameras with high fidelity. And this is an example of Aurora's in-house simulation engine in action. All this footage was created from our sensor simulation software. What you see is the same kind of simulated camera images the Aurora Driver would see. And when it comes to machine learning systems, they pick up on all sorts of details. And so we need to be very careful about constructing our virtual world to be a convincing stand-in for the real one. And so just a few things to notice. Notice the way the wheels spin and show the true smooth motion blur. The same goes for the road surfaces as we're spinning by. These are important details for our perception system. A blurry road surface appears very different to a machine learning system than a static one. Also note the reflections on the sides of the vehicles. These are true reflections. They're not faked. Reflected sensors return so-called multipath are important features of real-world operations we recreate in a physically correct world. When we pass a truck on the side of the road, which we'll come back to in a few slides, the driver is rendered realistically. It's really difficult to capture human motion. We'll just consider the uncanny valley. And we don't want to test and train our driver on humans that move like they're a 70s sci-fi robot. That's simply just not realistic. And the Aurora Driver might learn incorrect behaviors because of that. And our vehicles perceive the world through cameras, through LiDAR, and through radar. And so our simulations of each sensor modality must be physically realistic in order for our simulated experiences to translate into the real world. So let's take a look at simulations of each of the modalities in turn. Our LiDAR simulator factors in the true beam shape of each laser firing. We can handle complex effects like when the beam only partially covers an object, or when half the beam hits shiny car paint, and then the other half is hitting a rubber of a tire. Simulating radar is really difficult because of the way the radar waves behave. So quite often radar simulators, they just return arbitrary points on other vehicles, and they ignore the rest of the environment completely. So at Aurora, our simulated radar sensors actually work the same way real radars do. They reconstruct a data cube, and then based on the reflected radar signal, they accurately capture characteristics such as angular resolution and antenna gains patterns. On the camera side, our simulator factors in the true spectral nature of light and uses state-of-the-art path tracing and Monte Carlo integrations to compute each image, producing extremely realistic renderings. Finally, our First Light simulator, developed together with our in-house hardware team, is so accurate that we use it to evaluate hardware designs before manufacturing real prototypes. Next, we will look at how we use our realistic sensor simulation to complement and expand the data we're capturing on road testing. And you've probably encountered something like this while driving. stop car on the side of the road. This is a situation where long-range sensing is critical for autonomous trucking. We need to recognize and act on these situations much earlier than a passenger car would do. Every time we encounter an event like this in real-world driving, we capture it and we turn it into a simulation. But not just one, we expand it into a larger set of programmatically created scenarios that are variations from that original event. So in this video, you see first the on-road event that we're interested in. Then we see a side-by-side view of the automatically reconstructed simulation. And note that what we're interested in here is the event itself, not reproducing things like whether there's bushes on the side of the road or not. And finally, we see 4 variations of the exact same scenario, showing not just a truck that's parked on the shoulder, but also a passenger car, a box truck, and an SUV. And this is really the scale of simulation testing comes into play. We can generate as many permutations of this as we need to. And finally, these sensor simulations really become forever tests. While the data we have on-road might become outdated if we update sensors, this synthetic test can evolve with our sensor suite upgrades. So this saves us from having to redo all the work evaluating new sensor configurations. Here's another similar but real-world scenario that our trucks captured. This is a pedestrian walking their dog by the side of the road. Both the vehicle logs are on the left and then the simulation on the right. And so hopefully these examples start to give you a mental picture of the types and the complexity of scaling that we're faced with solving at Aurora. Stefano, from the AWS perspective, I assume you have a broader view on what's going on. Is that right?
Thanks, Tim. That was really, really interesting. And I love to see all the details, reflections, road surface, how does that really change in the terms of you compose the system. So hello, everybody. I'm Stefano Marzani. I'm the worldwide tech leader for autonomous driving in AWS. So let's go up a little bit and try to generalize, because again, we have some key industry challenges that autonomous driving face overall in the sector. The first is, and probably you noticed that in the team example and how you explain how rich simulation, data collection, and all these processes are, it's an hyperscale problem. So we have thousands of cores for development, terabytes of data flowing in the system, and it's really a petabyte, sometimes a hexabyte big data problem. And despite all this hyperscale, it requires agility and speed. Right? So these cycles has to be fast. If there's a bug, the code needs to be fixed and deployed quick. And that has to be done really at the speed of light. It was really impressive to hear the number 200, right, code modification that they are doing in Aurora, and how that is managed with agility and speed at the same time. And then cost. It's running all these cores, storing all this data, that has significant cost that needs to be managed, and that's another important aspect. And not to forget, we are in the auto space, so safety first approach. You can't put in the vehicle dangerous code that can really produce an unintended consequence. And then there's another aspect that is very peculiar about autonomous driving and automotive in general. There's no actor that can do it alone. It's an ecosystem play. Interoperability and seamless integration of multiple first-party, third-party workload-specific tools are the norm, are what's happening every day in these companies. And it's a software-defined problem. It's a software-defined vehicles. Probably you heard this term. It's a super important trend that tries to abstract the hardware of a vehicle from the software development cycle. And this is really structurally necessary to achieve this agility, speed, and consistency in managing these workflows. And then last one aspect, it's a global problem, right? Vehicles are everywhere on the planet. You may deploy vehicles in Europe, North America, South America, Asia, and you really need to manage that at a global scale, right? With security and data privacy at the same time. To support all of this and try to meet these challenges as AWS, we propose what is called an infinity loop, because it never ends, right? You see it here represented in the picture. I don't want to enter into the specific details of every service, of course, that you see inside the infinity loop, but you see on the left, we have our developers working on their desktop, hardware in the loop rigs, we may have a test fleet, production fleet, and all these elements exchange data with the cloud that is on the right side of this slide, this infinity representation, right? There we have ingestion, right? So we have services like Direct Connect or Outpost, Snowball that really brings the data in. And then you start to use this data. You may use AWS Glue or some ETL or EMR for big data processing, structure the data in databases like Dynamo, Aurora, or use OpenSearch really to look inside the data and scout for particular data. And all of this is data management, processes, and analytics. All these data and processes and procedure flow in what we call autonomous data lake that is based on intelligent storage and specialized compute, and is really a central construct in what AWS offers to its customer in this space. Because data is a corporate asset, probably the most important one in this sense, and has to be made available to all the business unit corporate-wide. And that's really an important part. When the data is there and it's managed this way, people can start to work on the data, right? Creating HD maps, for example, or performing labeling activities. And here we have our own SageMaker ground truth tool, or model and model and do algorithm development, deep neural network training, right, through SageMaker, that is our machine learning platform. And here inside the infinity loop, you see some acronyms like P3, P4, G4. These are different EC2 instances, so different computers, different servers that we have in cloud with different characteristics. Some of them have GPU for training, some others just have a powerful CPU. And this is very important, again, thinking about cost optimization, efficiency of the problem, that is one of our well-architected framework pillars, by the way, that is really to select the right instance for what you need to do purposely. And then you need maybe some specialized file system like FSx for Lustre, or specialized high-performance networking like EFA. And then you enter through important processes in ADAS AV like simulation and verification and validation that really take a lot of resources, right, inside the company. And here you have, again, the use of different kind of instances, and you can use specialized file systems as well. AWS provide as well what we call a development workspace, where we have a lot of tools to manage all these workflows or this procedure and all these data flows, right? Tools like Batch or DevOps, or tools to manage CI/CD pipelines, or tools to manage the workflow themselves, like our step functions, or the managed workflows for Apache Airflow. That is really important in autonomy. It's really, really important to manage and structure this workflow in a very, let's say, formal way through code. And there's another important aspect in all of this. And we love to say that it's a big loop as well. So it's not just an infinity loop. It's an infinity loop and a big loop at the same time, because we can't ignore what's inside the vehicle. And there are some important elements here to be considered. So when you, first of all, deploy the software, you want to maybe do what is called the shadow mode inside the vehicle. So analyze the performance of the software that has been just deployed in the vehicle and doing a testing shadowing, as we call it, and you see it on the left of this slide. And this edge intelligent agent that is inside the vehicle really needs to compare the performance of the software under test versus the software in production. And in this context, even the data collection needs to be intelligent. So given the huge amount of data that is flowing from the production vehicles, for example, to the cloud, maybe you decide to just get the data in specific context, specific condition, or when some conditions are met, like a disengagement, for example, or when the software under test and the production software has a disagreement, right? So in this specific condition, you want to maybe record some of the data and transfer just the data to the cloud, implementing a concept called snapshot. So infinity workflow in a context of a big data loop. But let's analyze a little bit more in details the three main workloads that we really see on AWS Cloud. The first one, I already spoke about it, is the concept of data lake. You see here, I won't enter into the details of each single colored box, of course, but I want to explain you the big picture of this service. So let's start from the left. You see here we have our ingest. We have cars running on the road. The cars can transmit data over the air, and we can have over-the-air ingest, and through, for example, Amazon Kinesis Data Firehose and IoT Core, or the data is transferred, physically through a direct connect or a Snowball device if the data is really in a large volume. And when the data is, in the cloud, we store this raw data in Amazon S3. The next step is really to start to use this data and perform some initial data quality check. Here we can use services like Amazon EMR to perform an initial quality check and just maybe store in a different storage class the low quality data, and in a hot storage just read the high quality, and we implement some form of cost management on the optimization. And then we can enter another phase that is, for example, the first analysis of the images that we collected on the road. And we do image extraction, anonymization. Here, for example, we see that we use a service like Rekognition, that is an AI service, it's a very simple API. You just throw in images in, and a Rekognition will give you back the plate or the face, and you can obfuscate them and produce an intrinsic privacy, right, on these data sets. And when you have that, you have a last step that is very important, annotation. So you can use your own workforce, you can have external annotators. Part of the data set needs to create these annotation labels that are used then to perform the training. And then as the next step, we really want to maybe just do some other analysis like scene detection. And you can have EMR, even in this case, processing this data and create additional data in an automatic way to select, for example, if a scene is collected in dark, in the night, or is collected during the day in a rainy condition or a specific geography. So you can really start, to give indication to your developers, data scientists, in how to understand this data, how to retrieve, how to use this data. And then you can have other steps, like you can synchronize the data better, you can do data enrichment, and add maybe through APIs, third-party APIs, further information to the data sets. And as a last step, you create a data catalog, and finally, you make this data available through, for example, AppSync with a search interface to the various people you have in your corporation, developers, engineers, data scientists, and so on. Please note, up left, we always have this managed workflow with Apache Airflow to really create and manage this orchestration. And then the other important workload is machine learning. Here we have 3 layers of services and offering. The first and basic one is machine learning frameworks and infrastructure with very common frameworks like TensorFlow, PyTorch, MXNet that are all managed in the cloud. And then we have machine learning service. I already mentioned SageMaker, and here we can have ground truth, SageMaker ground truth, SageMaker Studio IDE, Neo, very important to create a model in cloud and then deploy and manage the model on the vehicle itself. And then at the very top level, we have AI services with services like Rekognition that I already suggested before for plate and face recognition, and other services that can be used like Translate, Extract, and so on. You really, these 3 layers target different people. So machine learning frameworks and infrastructure, TensorFlow, are really for deep, competent person on TensorFlow or these low-level frameworks, while machine learning services can be used by developers. And AI service can be really used by everyone that can call an API. The way that these services enter into the play for, let's say, autonomous driving is first of all, as I suggested, for data labeling, and because you need to read to label this data. And here you can start to have an experiment management where researchers and data scientists are more involved. And here you can add the usage of on-demand CPUs and GPUs using managed processes. When you really want to scale it, and so when you have this, let's say, models more or less defined and workflows more or less defined, and you want to give them really to engineers in order to use these models and scale them out, you go with maybe on-demand or spot GPU instances and using managed training. And you need to provide tools to monitor these jobs and the profiles. And then you can deploy these models through SageMaker Neo, that is a managed implementation of Apache TVM, in the vehicles themselves with significant optimization. Of course, everything can be managed programmatically through the Python SDK and Boto3. Here it's very important. I already mentioned the importance of using a diverse set of specialized instances like P4, P3, that are our last generation instances for HPC and really to handle large distributed machine learning training jobs. G4 that have GPU and that can be used, for example, to render graphics. Inferentia, that is custom built by Annapurna Labs chip to perform inferentia and, let's say, for example, object recognition task in a very efficient way. And we even have FPGA instances that are really for specialized hardware accelerated application, like maybe simulating DSP or an image processor and so on. And then let's go through the final construct, big workloads that we see on AWS. First, it's simulation and resimulation. So let's analyze it. And you see on the left, here you have really the developers creating code, and the code becomes an artifact, and Jenkins managed the whole build and pipeline. And when we have these artifacts ready, we need to start the testing activity. The testing activity can be summarized two ways. Through an open loop workflow, again managed through a managed workflow for Apache Airflow. And typically in this case, please note, we get the data from the same Exadata Lake construct we already mentioned and analyzed. And we have this data pumped in the system under test, the artifact itself, in order to evaluate the performance of this system under test. The other workflow is so-called closed loop simulation. Here we have the management of synthetic data generated through simulators, engine that can run in cloud, and generate this data. The data is crunched in the system under test that will, in a loop, produce the results, for example, driving a control request to the virtual vehicle, and this will be the next step of the simulation. So in this case, we are talking about a closed loop simulation. Again, all the logs, all the artifacts, all the scenarios are managed and, let's say, consistently stored and logically represented in the autonomous data lake. And a little bit of details more in this closed loop simulation, as you can see here in the enlarged way. You see that for specific, here on the right, in the diagram, for specific tasks, we use specific instances. Because, for example, Tim mentioned it, right? There are various components in autonomous vehicle stack, like planning, control, perception, and so on. Planning and control doesn't require a GPU. So why in a closed loop simulation or in a simulation, we need to use an instance with GPU? We can use a Graviton instance like T3, right? That is a generic instance for us, and optimize cost without losing anything on performance. And the same thing, G4DN, as I described before, can use to render some of the scenes, right, and produce the synthetic data. So this is the reason why we call it closed loop co-simulation with proper instances. Why co-simulation? Because in automotive, there's never just one simulator. There are multiple simulators. Tim spoke about that when he discussed about the fact that, for example, you have to model a specific sensor like a radar, right? And here I have my last slide. Again, as I mentioned briefly, the AV partner ecosystem is really the approach to go. And in the last year and a half in AWS, we did a huge work really to help the ecosystem to nicely be integrated and work on AWS Cloud. companies doing, for example, simulation, like IPG CarMaker, SVL, LG SVL, or NVIDIA itself with their own simulator, and or company for really data management and processing or ingestion or labeling, like DSpace, B+, National Instruments, and so on. And I don't want to enter into the details, but to really see that's an effort. And it's one of the first questions when we start to discuss with the customer is, can you tell us what are your tools? How's your workflow? How can you help your ecosystem, right, to be efficiently run on AWS? So that was my general introduction to what AWS is doing for autonomous vehicle. And now back to Tim, so he can explain maybe how they use some of this service to build their infrastructure on AWS.
Absolutely. As Stefano mentioned, building self-driving products such as the Aurora Driver, it's a hyperscale problem. Our fleets collect massive and really rapidly growing data sets. And at the same time, these data sets are coming from more geographically diverse locations. Along with just the data scaling, our compute infrastructure needs to be dynamically scalable. We want engineers to scale the training and testing efficiently, so not every engineer has to become an expert in high-performance supercomputing and distributed systems, cloud, or even things like Kubernetes. And then as our organization, these data sets and all of the infrastructure scales, so too does our ability to model and predict and manage things like costs and security to run all of these workloads as efficiently as possible. And each component of our development platform, they need to work holistically together. More specifically, our data engine is our platform for collecting, searching, labeling, training our ML models in a flywheel that uses model and system performance metrics to continuously improve the quality of our data sets in the most efficient and the most impactful way. So the fast iteration cycle provides engineers with the information they need to rapidly advance the capabilities of the Aurora Driver. We also leverage these tools to tackle this long tail of autonomy effectively. With each new capability that we build the Aurora Driver to handle, we can use the data we've already collected to accelerate feature development rather than recollecting data each and every time. So this tight feedback loop from model and system performance back to data sourcing and labeling, it allows us to continuously improve our data sets in the most efficient and impactful way. Now, obviously, we could do entire reInvent talks on each step, so let's dive a little deeper into the massive compute we leverage to give engineers that feedback and to validate changes before we ever drive a single mile. You might recall this diagram of moving fast. Mature, high-fidelity simulations running at scale, like the ones we showed earlier, they allow us to test and train our ML-based perception and motion planning systems reliably. This is equivalent to having a fleet of 50,000 trucks that can be deployed basically instantly at the touch of a button. This has many more benefits, but more than anything else, it's about moving faster. So let's go deeper into what's that button push actually look like. You can think of this really as Aurora's virtual supercomputer that we built on top of AWS. This is the real workhorse for computations across Aurora, including many of the simulations that we've shown. But also, we develop our Atlas HD maps and testing perception scenarios or simulating various sensors, all run on this virtual supercomputer. So we're going to walk through how an engineer might test a change on the Aurora Driver. An engineer can manually run a sim based on a UI or a CLI just on demand. They want to test one specific situation. But we also have simulated tests that just run on a routine schedule. So every given period, we run a series of executed sims. But then any code that's changed, such as an ML model or some other part of the code base, that triggers an automatic set of simulations to measure whether we're regressing or whether we're progressing the Aurora driver to better handle those situations. So this fully automated trigger, then what it does is execute our monorepo's CI/CD process. And this hermetically builds and tests our code using our build system. It's an open source tool called Bazel. And our CI/CD system then builds any needed artifacts on top of that code commit, such as containers. These automated jobs then spin off and they create offline tests. And they can have a range of execution steps to run on our scalable compute system called Batch API. And these are capable of scaling computations over extremely large directed acyclic graph jobs. So for closed loop simulation, besides the execution steps, an engineer might specify different computational sizes, GPU acceleration or CPU, or even degrees of parallelism that they need to execute the workload. This infrastructure is built for multi-tenant workloads across the organization. Like I said, we have maps and simulation and many different workloads. So any given day, we can see jobs needing to run thousands of GPUs and hundreds of thousands of CPUs on the back of commits as engineers are making changes they want to test. So this is extremely dynamic and to give this real-time feedback to the engineer. And because we need to go quite a bit over the roughly 3,000 nodes a single Kubernetes cluster that the control plane can handle, we use several clusters. And so Batch API is how we create a simplified front-end platform. And this API just obscures to our engineers so they can easily scale these computations. They can even be so large they need to run across clusters. But it also helps them debug and monitor them from their laptop or from any AWS account inside of our organization. And the custom Batch API autoscalers that we've built, those really do the heavy lifting of scaling up and running workloads across a range of instance types, even bare metal, and then adding nodes to the Kubernetes control plane so they can utilize them. They also attempt many different availability zones and spot availability. And at the same time, the clusters are running many other sizes and shape workloads for many other users, all isolated by their Kubernetes namespace. So it's a true multi-tenant cloud infrastructure. Then on top of that, remember we have this thing, we need to track things like costs. So we have a custom cost tracking that exposes the economics of the specific jobs that are being run by different teams. And what we're really trying to do is let the teams make smarter decisions. Finally, job metrics are written back to RDS that's usually fronted by an API. Usually it's a gRPC API where metrics then get recorded and they can be absorbed by dashboards. These could be Grafana, or often we have business-friendly front-end dashboards such as Periscope. So we get real-time information back to the engineers, how that change actually impacted our tests. So this provides easy to consume feedback across the organization, and we get this before we ever drove a single mile on the road. For one example, the sensor suites on our trucks, we developed them and iterated on them in the lab and in simulation. Then we built almost 20,000 truck simulation scenarios before we ever completed the first real-world prototype. So the Aurora driver is developed against the scenarios in the cloud and was ready for real-world testing on the first truck as soon as it was ready. So hopefully that gives you an idea of the workflows an engineer at Aurora would use the cloud. But what are some of the things we've learned by scaling up and building these types of systems? Well, a few have come to mind. First, using all the availability zones inside a region. This has been absolutely critical for us when we're scaling at these types of capacities. Second, is many instance types, and especially having larger scale nodes, are incredibly helpful when you're running these loads in Kubernetes. Larger nodes mean less IPs, so that's very important. We even use metal instances, but we do try to mix across a range of the larger scale instances. Then Spot. We use a lot of Spot capacity, and we use it every place we can get it. So that's, again, factored into the custom autoscaler that we've written. Burstable workloads. These can be incredibly taxing and challenging on the Kubernetes control plane and etcd. So you need to be very cognizant and make sure you understand the dynamics of the scaling and how it's going to impact Kubernetes and clusters. And then last, we really learned quite a bit on how we need to prep our accounts and our account limits, things like VPC CIDRs, and being able to scale up those control planes so that we can handle those types of workloads. So these are some of the things we've seen. Stefano, you talked to a lot of customers. What do you see?
Absolutely, yes, Tim. I can surely provide an overall conclusion and see how do we see things all across the sector, automotive and autonomous driving, let's say. So the first conclusion is autonomous system development is an hyperscale problem, as we saw very clearly, that requires at the same time agility and speed, attention on cost management, and enforcement of hard safety requirements. Super important, priority 0. AWS, of course, provides a complete set of services to support the main autonomous driving workloads that are data storage and management, machine learning training, and simulation. And important to remember, it's not just cloud service that stay up in the cloud, but it's necessary, really necessary, to integrate the vehicles in a big loop perspective, as we defined it, with shadow mode, so maybe monitoring how a software at the edge performs, or through snapshot, meaning collecting data in an intelligent way, and in general, using an intelligent edge approach in this big loop with an infinity workload attached to it. And then autonomous driving is an ecosystem play. And we want to be the most ISV-friendly cloud provider on the market with AWS partner network opportunities and AWS marketplace opportunities. So that concludes our talk. Thank you very much. It's been great, honestly, even at the personal level, preparing this with Tim and with the Aurora team. So thank you again, and talk to you soon.